Yes, Keynote, when you are in presentation mode, allows you to pass transparencies with the mouse, just clicking left to pass forward and right button to go backward. Wow. And it's super handy, that. And I've never managed to get that that kind of option with a normal PDF presenter program.
I see, yeah.
This is why I like it like that, but otherwise it's the same.
I usually use the remote control that I use in person, just to feel like an in-person experience.
Yeah. I would suggest to the students they connect their camera, at least few of them, so I see some faces, you know.
Yeah, so really please,
yeah.
Let's make it less awkward.
Yeah.
So we...
half of them with masks though on the face, but
at least you see the eyes.
At least I see something. Somebody nodding.
You don't feel you are talking to a screen, right? You're talking to people. It's
exactly.
Nicer. Very good. Okay, so I think it's about time to start because it's 2:35.
Okay,
so,
excellent.
Good afternoon, everybody, and welcome to the last lecture of the last day of the last week of the school. So the very last lecture of the school. We have the 5th lecture by Danny on gravitational wave backgrounds. So go ahead whenever you're ready.
Thank you so much. Okay, so welcome back, everybody. This is indeed the last lecture of the series of lectures on gravitational wave backgrounds, and we are also closing the school, so a bit sad, but let's make the best of it. Outline. What have we covered so far? No, we covered a first block with definitions on cosmology, general relativity, and some hardcore definition on gravitational waves. We covered a second block on gravitational waves from inflation and from preheating. And then we started covering a third block yesterday, including gravitational waves from phase transitions that were actually happening either in the thermal universe or also during the reheating era. And part of that third block is also the idea of a gravitational wave emission from cosmic defects, which is what we are going to cover today. Now, this is the whole scheme of everything we've covered in the school. Cosmic defects are a potential consequence of phase transitions. And as we will see, there are two types of gravitational wave emissions that can be associated to cosmic defects. But maybe before we enter into the actual gravitational wave radiation, let us actually discuss a little bit about the physics of cosmic defects themselves, which essentially is like part of discussing phase transitions. So cosmic defects, these are a possible aftermath product of a phase transition. Now we are going to follow actually one of the pioneer paper by Tom Keeble, in which he actually introduced cosmic defects in the literature, and ever since they became a really interesting topic. No, just following the abstract of his pioneering paper, what Keeble said is that possible domain structures can arise in the universe whenever there is spontaneously broken theories, no? Spontaneously broken gauge theories, although in reality they don't really need to be gauged. No? So what Keeble really states is that whenever there is a symmetry group G, that is a symmetry of your theory, if you spontaneously break this group into a subgroup H, then of course you are gonna form what we call a vacuum manifold, or the coset of H in G. Okay, H is like the remaining symmetry you have, so the unbroken symmetries, and the vacuum manifold are like the space corresponding to the symmetries that you broke. So essentially, whenever you have a situation like this is precisely at the mathematical and physical level what a phase transition is. He predicted that it is possible that some kind of domains, topological domains, will emerge in the universe. And as he said, this depends on the properties of the vacuum manifold, specifically on what is called the Omotopic groups, which characterize the actual topology of this vacuum manifold. So why Keeble introduced this idea? It's subtle, but in reality it makes all the sense, no? It has to do with causality. So imagine you spontaneously break a symmetry, whatever this phase transition represents. This means there is a Higgs-like field that takes expectation value, represented here by this radius in red. And there is a given direction this Higgs field takes in the internal manifold, in the internal field space, no? But in different regions of the universe, once you fix a system of coordinates, of course, the direction of the Higgs field within its own manifold, it's gonna be random, no? Like if I have a region here and this other region is causally disconnected, it's not possible that this region knows anything from the direction of another region sufficiently far away. So the whole point is that when a phase transition happens in the universe, it happens everywhere at the same time, but that means also it happens at regions that are causally disconnected. And then that means that the vector representing the direction within the internal manifold of the symmetry breaking essentially is going to be kind of random when you compare it at different regions. Now the question is, what happens in the interface of those regions? What happens in between those regions? And this is where Keeble realized that certain kind of structures that he called domain structures or topological defects are gonna appear. And essentially what controls that is the so-called Omotopic groups of the vacuum manifold, which essentially characterize what is the topology of this manifold. We are not going to enter into the details of this, what mathematically this means, but of course, I'm happy to discuss about it at the very end of the lecture if somebody is curious. So let's look at this from a physical point of view. Imagine a Higgs-like sector, okay, which we typically represent with a Mexican hat potential, or it could be something else. The thing is some effective potential that represents there is a set of new vacua at which the field is gonna want to transit at some moment. And that's controlled by some interacting Lagrangian. What we've seen is examples in the lectures that these interactions could be due to interactions with the thermal background. This is what controls typically a phase transition in the thermal era, but it could also be due to interactions with a field. This is what we saw in preheating. In either case, due to the dynamics of this interaction, at some moment you trigger the development of this new vacua, and then the Higgs wants to go there. So let us represent this in one location in physical space. I take a two-dimensional cut of a space, X and Y variables, and then we place the Mexican hat potential in different regions, say in the positive corner, in the positive negative corner, negative negative corner, negative positive corner, okay? We place this internal vacuum manifold there, and then we make the Higgs to take arbitrary directions. So we take them opposite here for clarity. Now bring those vectors of the Higgs field, which is directions in the vacuum manifold, okay, in internal space, and bringing them to the same spatial location, which is the center of this system of coordinates. Now, I need to make my field continuous because my theory is about continuous fields. So how can we do that? Essentially, somehow there has to be a rotation of this Higgs field vector such that we, if we were in this corner of the region, we were pointing in this direction, and in this other corner, we are pointing in this other direction, the field has to rotate in between the regions, and so on and so forth, all right? But if you think about it twice, you know, okay, first of all, we need this rotation for continuity reasons, obviously, because the strength or the length of this vector in the internal manifold is the BEV, so it's the same. But what happens at the origin itself? You know, the only way to make continuous your field is that actually you make your field go back to the vanishing expectation value. So it's like you make your field climb up to the top of the Mexican hat potential, which is a very energetic situation. It's not favored, no, by typically, you know, if you let the free fields, but now they are in interaction, you have to make them continuous. So essentially the dynamics forces, in order to make the boundary continuous, the field to climb up here. So there you get the idea that you're going to have a large concentration of energy, because there's going to be regions in a space where the Higgs is forced to take the maximum potential energy. So those configurations in a space can be of various kinds. They can be elongated configurations, all along which the Higgs is taking this vanishing value inside and hence maximizing its potential energy. Or they could be like a ball-like structure. These are called monopoles, the previous ones strings, sorry. Or maybe they don't have a shape, but they still represent a texture with changes of the direction of the gradient in internal manifold, which still has a lot of energy due to the gradiental energy. So essentially, it is the microphysics, in particular the topology of the vacuum manifold, what determines what is the actual object that emerges. And depending on the topology of that vacuum manifold, we have different cosmic defects. Let them be strings, monopoles, textures, or even something called domain walls, which are typically forbidden if those are the only defects you form. So there are a zoo of different guys of this kind, no? Of different cosmic defects, which include these categories: domain walls, cosmic strings, cosmic monopoles, or non-topological textures. Now, all of them are created due to the fact that there is causality, and the microphysics then determine what is their typology. But also, due to causality, necessarily there has to be some kind of correlation length. No, because when you form them, it's at the boundaries of these configurations you've created when you spontaneously break a symmetry. So there has to be some scale associated to that. And because the physics is causal, because it's bounded by causality, there has to be some correlation length that characterize the typical distance between these objects. And this correlation length, of course, can only be a fraction at most of the causal distance, which is the Hubble radius. So essentially, if you think of monopoles, for instance, this correlation length determines the typical distance between them at formation. And later on also, it evolves in time. If you think of strings, this could be like the cross sections of the strings. The strings are coming transverse to the screen, and this is the typical distance in between strings, and so on and so forth. If you think of non-topological defects, this will be the scale characterizing the gradients of them. Now, the great insight of Kibble was not only to realize that you form topological defects upon spontaneous symmetry breaking in global and gauge theories. He also understood, with very clever arguments, that once you form them, they are going to enter into what he called the scaling regime. The scaling regime means that this fraction I was referring to before of the correlation length compared to the causal horizon, it's actually constant at every moment. And not only is constant, it's of the order of the horizon. So essentially what he understood is once you form this initial network of defects, whatever they are, now they are going to start evolving as a network, and they are going to maintain a correlation length that is growing essentially linearly, following tracking, if you want. That's why it's called a scaling. It's a scaling with the Hubble radius. Therefore, for instance, if I want to characterize at any moment in the expansion history of the universe, at any moment there is a network of cosmic defects, and I want to characterize what is the typical momenta, I know the typical momenta, I can just normalize it, say comoving momenta, I can normalize it by comoving Hubble rate, or if you want conformal time, inverse of conformal time, because that's the scale at which we have the characteristic length scale, our correlation length. Pictorically, I think this is very clear from this picture. As the universe expands, the Hubble scale, the Hubble radius is growing linearly with time, and so it is the correlation length of the defects. Essentially, the defects correlation length is adapting itself all the time to the causal distance in the universe. Okay, so far so good for what the cosmic defects are, more or less. Let's start talking about some emission on gravitational waves. First, we're going to make a general remark about the stochastic backgrounds. Now, remember that we have a master formula for the energy density of gravitational waves, which is given by the power spectrum of the velocity perturbations, which is the expectation value of this bilinear combination of the tensor perturbations. Okay. If we define, for instance, this conformal redefinition of the tensor perturbation, then we can write the equation of motion in this simple form, which is a quasi-harmonic oscillator now, because I only have a frequency term. Essentially, with this, I made disappear the friction term. And why do I do that? Because this allows me to write in a simple manner the solution of the time derivative of the tensor perturbations as a convolution of the source, the transverse traceless part of the anisotropic stress, convolved with a Green function in time, where the Green function, you know, is the operator that characterizes this wave operator here. So this Green function is associated to the solution of this wave operator here. I'm not gonna specify the form, or yeah, maybe we can do it a little bit. So essentially what's relevant here is that since I know what's the solution of the derivative in terms of Green functions, I can write it here. I can now rewrite my power spectrum of derivatives of the tensor perturbations as a product of two Green functions, two time integrals, and then this object here, which is the expectation value of a bilinear product of the sources. So you see, I have two pieces of the transverse traceless part of the anisotropic stress. I take the expectation value, that's what defines the power spectrum, if you want, and we build this guy. This guy is called the unequal time correlator, for obvious reasons. Unequal time because it's at different times. So in this case, it is a correlator at different times, and a power spectrum from the point of view of momenta. So essentially, what this means is that now I can re-express my energy density spectrum of gravitational waves in terms of the in terms of the source spectrum. First, we need a small trick, which is we need to take some time average over the Green function, because these are highly oscillatory. And when you do that, essentially, you write, it boils down to write this cosine here, this harmonic function, times the scale at which you are and the Hubble rate. So altogether, essentially, if you want, the power spectrum of time derivatives of the tensors can be rewritten in this manner as a function of the unequal time correlator, which essentially allows me to write the energy density spectrum of logarithmic modes, the logarithmic energy density spectrum of gravitational waves, as a double time integral over expansion history times this combination of Green functions times, or this harmonic function coming from the Green function, times this unequal time correlator. Okay, so essentially, obviously, the statistical properties of the background of gravitational waves have to be encoded, obviously, in the history of the statistical properties of the source. And the statistical properties of the source is this unequal time correlator, which corresponds to the 2-point function of these guys. Okay, hopefully this is clear enough. Let's use this now to work out what is called the irreducible background of gravitational waves. So, cosmic defects are going to be naturally a large source of gravitational waves because they are made of large gradients of the field configurations. They are made of gradients of scalar fields, if this is a global symmetry breaking, and they're going to be, together with the gradients of scalar fields, gradients of gauge fields, which are magnetic field configurations, and time derivative of gauge fields, which are electric fields. all of these guys, remember, are a source of gravitational waves as long as they have a non-trivial transverse choiceless part, which certainly is the case here. So essentially, we need to compute the unequal time correlator of a defect network. So if you have a defect network, you can associate some energy momentum tensor through these terms to your network, to your actual defects. If you know how to compute the transverse choiceless part, you can try to compute, if you are clever enough, the expectation value of this bilinear combination, which gives you the unequal time correlator. So the energy density gravitational wave spectrum, it's actually given by this master formula for any stochastic background with sources. And certainly a network of cosmic defects, what happens is it's emitting gravitational waves. So it's acting as a source of gravitational waves all the time as the network goes in scaling in the universe. So the question is, what do we plug in here for the unequal time correlator? An interesting thing, well, first we determine that this is comoving scale and conformal time. And the interesting thing is that once you are in scaling, since your solution of the dynamics of the distribution of defects, it's always tracking the horizon, this implies, scaling implies, this is a consequence of scaling, that the unequal time correlator can only take this form. Any scale dependence must be normalized to the comoving Hubble rate, which is nothing else but the inverse of the conformal time. So essentially, any unequal time correlator of any objects in scaling must have a form with the scale dependence normalized in this manner, in this fashion, with time. And due to dimensional considerations, we invoke the vacuum expectation value BEF here to the fourth power. And we are, because these are bilinears in the fields, okay, so that's the natural units. And we are forced to take some square root of product of times in order to make this dimensionally correct. So essentially, this means that I can plug in here in the unequal time correlator part, I can plug in this functional form, even without having done any computation, just because I know the defect network is in scaling. So let me evaluate this now in radiation-dominated universe. So in the early era of the universe, before transition to matter domination, so during radiation domination, the scale factor in a conformal time is linear in time. So I just plug it there, okay? I plug it linear dependence in time, and now some magic happens. Look at this expression. I have a k to the 3 power here, which I always have due to volume element to define the energy density spectrum. I have a double time integral, 2 powers of time, a dimensionless function because k times time is dimensionless, and another dimensionless function here, which characterizes the unequal time correlator, times some square root of a product of times. So essentially, if you define dimensionless variables, this k comoving momentum times conformal time, you can rewrite this integral in such a way that it only depends on these dimensionless variables. Okay, just introduce the k to the 3 here. You take 2 powers of k to compensate here for the elements. And if you write a square root of this product of times and eliminate this square root here, essentially you absorb the last remaining power of k. And then the cosine here is written directly in terms of these dimensionless variables. And this function here, u, is also written in terms of those dimensionless variables. So, surprise, all of a sudden we've written a dimensionless equation, a dimensionless expression. So this is constant. If you integrate over sufficiently large upper bounds, so k times time much larger than 1, this converges, the integral becomes insensitive to the upper bound, and then this becomes a constant. So what I'm predicting here, without having even done anything, just understand what scaling implies, is that any network of cosmic defects, because they are in scaling, necessarily they emit an energy density spectrum of gravitational waves, which is a scaling invariant, constant in amplitude, during or meanwhile those modes are being emitted at radiation domination. which, as you know, typically for direct detection observation are the interesting frequencies. The frequencies correspond to this era. So essentially, you see, we are predicting that there is a universal functional form characterized by the energy scale to the fourth, the BEF to the fourth, suppressed by Planck mass here, and times a constant that is characteristic of the type of cosmic defects. So for strings, monopoles, or textures, you are going to have a characteristic function here, U. This function typically has to be extracted from simulations. You plug it here, you do this integral, this gives you a number, you plug it there, you get the amplitude of your background. And this happens for any kind of phase transition. It's not relevant what's the order of the phase transition, and also happens for any kind of defects. All it matters is that they are in scaling. Okay, so this is like a general theorem. What is the total spectrum when I take into account that the universe enters finally into matter domination and later dark energy dominated phase? Well, then the spectrum is built from two pieces, the constant part from the modes emitting during radiation domination, and a scale dependent part coming from the modes emitting during matter domination. The part of dark energy is completely relevant because it corresponds to so cosmological long wavelengths that is really relevant for the purpose of this spectrum. So I just have two pieces, one from the radiation dominated era with this constant characterized by this integral, and a scale inverse power law of K dependence times a constant, which comes from this other integral, which is also a dimensionless number, with the corresponding unequal time correlator in scaling units for matter domination. So essentially, we've done simulations, for instance, of a global breaking of ON into ON minus 1. And then we extract the unequal time correlator. We write it in scaling units, check that there is a scaling in the simulations, then plug it in those expressions before, these expressions, and then we can characterize the spectrum. So the spectrum has a plateau, has a rise up power as K2 minus 2 in the infrared, and then finally you hit the horizon here and you go as K to the 3 all the way down to infinite, to zero frequencies. So the dark energy would only modify the tail here. This is why it's irrelevant. All it really matters in reality is not even this bump, is the fact that there is a plateau. Of course, the height of the plateau is controlled by the BEF. And here you have how it scales with the BEF. Unfortunately, it scales as a power law to the fourth power, which means in the moment you kill the BEF way below the Planck mass, you kill your signal. But for GAT scale BEFs in phase transitions, this would be still observable, for instance, presumably in LISA, Einstein telescope, and other experiments. I've got to say that there are actually quite a few works recently in the literature, because so far these results are from a few years ago. But in the last 2-3 years, there's been new works on this by other groups, and they don't completely agree with the scale invariance, because they claim that in the lattice, you can measure a deviation from the standard scaling through a logarithmic deviation. Now, if you extrapolate the logarithmic deviation they measure on the scales you capture in the lattice to cosmological scales, this translates into a scale-dependent background, and this is what these papers are predicting here. I'm not going to enter into who is right, who is wrong, because we don't know. Okay, this is just to give you an idea that this is a hot topic that people are discussing, and people are so far not agreeing so much about it. And global strings are actually very relevant for Axion network of strings, axionic string networks, which are a consequence of dark matter Axion models. So essentially clarifying what is at the end the final spectrum, a scale invariant or with some tilt, and what is the final height, it's going to be a relevant topic in the next year, I'm pretty sure of it. Well, good so far for our discussion about the scaling or small violations of scaling, as the other research works are claiming. what about now the particular case of cosmic strings in general? Okay, because so far, how to say, sorry, maybe I wasn't very clear here. Here I was discussing all kind of defects. N equal 2 means cosmic global strings, N equal 3 monopoles, N equal 4 textures, N equal 8, 12, 20. It means how many components your Higgs multiplet has. Okay. Now these works only concern global strings. Okay, this claim of deviation from log scaling is only for global strings. So let's focus now on strings in general. Let them be global or gauge. Now, when do cosmic strings in particular form? Well, we know we need a phase transition. I think that should be pretty clear by now. We know this phase transition is characterized by a symmetry breaking pattern from an original symmetry down to a minor symmetry. We know this manifests in space as nucleation of bubbles that expand and collide. But now we've understood that in between the boundaries, there are configurations that cannot be undone due to the topology of the vacuum manifold. And what's the topology we need? Well, technically, this is called the fundamental Omotopic group. We need this group to be different than triviality, than unity. So essentially what this means is that whenever you have a vacuum manifold where you can trace a circle continuous of your Higgs field configuration, like here, but you cannot shrink it, okay? It's not possible to shrink this, circle. This is precisely what this condition means. You are expecting cosmic strings to be formed. So to give you an example from some simulations, actually from my PhD thesis, these were a small scale simulation, but still capture very well the essence of forming cosmic strings. Here we see the cosmic strings in pink. These I'm calling them Higgs strings because it represents the minimum of the Higgs. No, the Higgs has to climb up on top of its Mexican hat potential, so it goes close to 0, and therefore is the maximum potential energy, this configuration. They are very energetic configurations. And now here I'm plotting the phase in the internal manifold of the Higgs, which was this corresponds to the breaking of a U1. So it's a complex Higgs field with real and imaginary parts. I can define a phase. And here what you see in colors is how the phase rotates in one particular location of a string from 0 to 2 pi. So you see precisely the phenomena I was referring to before pictorically, but this comes now from a real simulation where spontaneously we've created cosmic strings upon a symmetry breaking of a U1 gauge symmetry. And I say a U1 gauge symmetry because actually we have gauge fields, and correspondingly in the same location we had the maximum potential energy of the Higgs configuration. We also have the maximum energy density localized of the gauge fields. In this case, for instance, here I'm plotting magnetic field energy density. I could do the same with electric field. Okay, so you see, they are, it's a very simple realization of field theory. And even though we don't know if there are topological defects out in the universe, there is nothing strange about them. They just don't happen in the standard model. You need beyond the standard model physics, because for instance, the electroweak symmetry breaking in the standard model without any extension of the standard model is the breaking of SU2 cross U1 down to another U1, and that therefore don't give you the fundamental Omotopic group to be different than triviality. And hence there are no cosmic strings expected from the standard model. However, if you modify the standard model or you go to some grand unified theory framework, it's very natural to have actually cosmic strings. So if the effects are cosmic strings, the reason why actually most of the time you hear in the literature or you hear people talking about gravitational waves from cosmic strings and not just any cosmic defects is because there is a further emission associated to the fact that the defects are strings. Why is that? Because cosmic strings have a very nice property which is called intercommutation. They can self-intersect themselves and chop off a loop. or they can intersect between two of them and chop off a loop and then disconnect two long strings. So essentially, what is special about any network of topological defects that are in the case of strings is precisely that they can produce loops. And now, what are these loops? These are huge rings of high energy density, so a huge concentration of energy. And these guys are like an entity by itself, okay? It's formed by this topological obstruction of the field to go to the vacuum manifold, but they have a lot of energy. So essentially what they are gonna do naturally is to vibrate. And when they start vibrating, if they have any kind of, let me call it defect in their shape, these are called cusps or kinks, okay? This is particular features in the actual realization of each string loop, which naturally occur because they are formed from intersections of other strings. What's gonna happen is they vibrate and they are gonna emit in the region of these features, they are gonna emit a large amount of gravitational waves. So essentially, cosmic string loops of a given length L, they naturally oscillate because they have a huge tension, just because of all the energy they have. And that essentially predicts that you are going to emit gravitational waves in a series of harmonics of the oscillatory period. Okay? So this is actually the original emission of gravitational waves that was first uncovered and discussed about gravitational waves from cosmic defects, in particular from strings. And actually, it's like 30 years older than the other one I was telling you about. So it is this emission that actually makes cosmic string networks very appealing, not only because cosmic strings are possibly the most appealing type of cosmic defect, also because they have this mechanism of producing gravitational waves, which other defects don't do. So essentially, this is going to be an emission extra from the point of view of the irreducible background we were discussing from the scaling network. So the network is in scaling, it's emitting gravitational waves. And on top of that, since they network chop-offs loops, those loops are gonna radiate more gravitational waves. So people have worked out formalism within the years. Essentially, this formalism is telling us that the energy density spectrum of gravitational waves, it's characterized by its proportional to the tension square, to some constant that you actually can kind of predict analytically order of magnitude or measure from numerical simulations. And then you integrate in the cosmic history and you integrate over the loops that you have in every moment, no? So you have an integral in time over the cosmic expansion history, and you have an integral over the loop number density at every moment, characterizing the distribution of loops of different sizes L at every moment time, at every instant of time t. And of course, then you have the emission associated to each of these loops at every moment, okay, at every moment in time. Very important is to realize that this loop number density comes from what is called Nambu-Goto simulations. I will say in a moment what Nambu-Goto means, but first let us realize that in this expression you have to plug in here what is the power emitted, gravitational wave power emitted per loop, and essentially you can compute analytically that this should scale as a power law of the frequency and the length scale of the loop with a given exponent, which depends on the features, kinks or cusps that you have in your loop. How to model now the loop number density? Well, there are different approaches. In this paper, we refer to these approaches as modeling 1, 2, and 3. In model 1, essentially, this is the historical approach where people were taking an analytical arguments based on scaling, and they were guessing some coefficients. In model 2 and model 3 are, however, based on calibrating the loop number density in scaling units from actual simulations of Nambu-Goto strings, which, as I said, I will describe in a moment what they are. So model 2 and model 3, they take input directly from Nambu-Goto simulations in an expanding universe. Unfortunately, as you will see in a moment, they don't agree so much in the loop number density. Whereas analytical approach, typically nowadays, it's considered more of a toy model that is calibrated in light of these simulations. Now, what about lattice field theory simulations as opposed to Nambu-Goto? Okay, and I'm sorry because I'm realizing I should have said what Nambu-Goto is already, but the transparency comes afterwards. So lattice simulations are the ones in which you realize in field theory the actual symmetry breaking pattern, and you see the defects in the same manner I was showing you in my previous three-dimensional box simulations. And here is one example of that by a colleague of mine. Now, the problem is that in simulations of field theory, we do see the loops form as expected, but they actually open a new decay channel into radiation of scalar and gauge fields, so the same fields they are made of. And essentially, the consequence of these loops disappear rather fast. And this is very confusing because in the Nambu-Goto picture that I will explain the next transparency, these radiation channels are not expected. They do not exist. So the point is that when we do field theory simulations, the only background we can really capture is the irreducible gravitational wave background from the network in scaling. Because the loops decay so fast that even though they contribute to some emission, they don't sustain sufficient number of oscillations, and then they don't really build up the loop number density that people infer from a Nambu-Goto simulation. So the next results are all based in Nambu-Goto, and Nambu-Goto is nothing but taking the limit of infinitely thin strings, where you really consider they are infinitesimally thin, so there is no width. And this is supposed to be, of course, a very good approximation to a cosmic string network. So a network of cosmic strings in the universe, because of course the physical width of a cosmic string is really given by the inverse mass scale of the symmetry breaking field involved. But the typical distance of the cosmic strings, because they are in scaling, is typically the Hubble radius, which obviously becomes a macroscopic length scale compared to this microscopic length scale. So in principle, the approximation of a cosmic string network by Nambu-Goto, at least in the so-called local strings, which are the ones arising when you spontaneously break a gauge symmetry, should be pretty good. But in any case, I insist that, however, when we do abelian Higgs simulations, that is a specific realization of local type of strings in field theory, we do not see the standard prediction from Nambu-Goto. Well, there is a huge discussion in the community. It's an unsolved problem. So what I'm going to do next is assume Nambu-Goto is correct. And based on this, we will place some constraints and observability of cosmic strings. So remember that the energy density spectrum of gravitational waves is given by this integral over the expansion history times the loop number density that you need to extract from the Nambu-Goto simulation, which characterizes at every moment in the history of time the distribution of loops. And then you multiply by an average power emission of these loops, which is just a power law. So if you use that machinery, plug in your ingredients for the simulations, what you get is a spectrum of gravitational waves of a background from the loops versus frequency that looks again like a plateau coming from the modes emitting during radiation, and a bump coming mostly from the modes emitted during matter domination, or from loops that were formed during radiation domination and keep emitting in matter domination. Okay? So it's very similar to the shape of the spectrum I already showed you for the irreducible background, but it's not the same spectrum. It's completely different. The shape of completely different, not in shape or in form, but the physics behind. The physics behind also has to do with the fact that depending on the size of the loop in these units alpha relative to the horizon, so this means 10% of the horizon size at the moment of birth, this means 1%, etc., 1 per mil, etc. So depending on the size of the loops at the moment of birth, when they are, disjoint from the whole network of cosmic strings. This determines also the amplitude and the shape of the spectrum. However, it's true that the latest simulations, which are the biggest simulations on Nambu-Goto strings, essentially they signal finally a universal size for the loop length scale, typical length scale at the time of birth when they are formed, which is 1/10 of the Hubble scale at every moment. So this is good because actually that favors us to enlarge our signal. Now, as I told you, there are two modelings of the loop number density from different simulations, the Model 2 and Model 3 in our paper, which is becoming a reference paper because it's from the LISA collaboration and we summarize all the models that are in the literature. And in Model 2, when you do your math with the loop number density, they infer from the simulation. The spectrum always looks like this with the plateau and then the bump. In Model 3, however, sorry, 1 second, guys. In Model 3, however, we do have the plateau at larger scales, but we have some features at intermediate scales due to features in the loop number distribution they infer. And then finally, they see the bump going down finally, but they do have this different shape. Who is right, who is wrong? Well, it's an eternal debate in the community. I'm just showing you both results. Luckily, both of them show that their predictions are capable of probing the tension here in units of Planck mass inverse, so G mu. Tension is dimension 2 guy, so G is dimension -2, so this is a dimensionless number. So this is like, if you want, this is roughly speaking like the BEF suppressed by the Planck mass square. So essentially, they can probe with an experiment like LISA, for instance, a very large region of parameter space that right now is not under exploration, which essentially is like 6 orders of magnitude of range of this parameter, which is the tension. Okay, time's up. Let me finish this first part. So the minimum tension they can probe is like of the order of 10 to minus 17 in Planck units. How good that is? How good that is? So essentially this corresponds to a BEF of down to 10 to 10 GeV. So you see we are kind of closing the gap now with colliders that are reaching above the electroweak scale significantly now, few TeVs. So the CMB constraints on the tension is 10 to minus 7. Constraints from PTAs today are 10 to minus 11. In the future, they cannot get better than 10 to minus 14. An experiment of LISA either will detect gravitational waves or will improve 10 orders of magnitude constraints from CMB. 6 orders of magnitude constraints from current PTAs, or even 3 orders of magnitude better from the best PTA measurements that will ever become available into 2030s. So these are really the best constraints we can get in cosmic strings once these kind of experiments go, like LISA or Einstein telescope, and they have a huge potential of discovery or to put significant constraints. And to finish before the coffee break, let me just show you that really the spectra from the string loops, even though it looks similar to the spectra from the scaling from the infinite strings in this case, is just qualitatively because the amplitude of the gravitational wave background from the loops is actually less suppressed in the BEF than the spectrum from the scaling network. So this background from the loops is much more powerful. Okay, and I think we're gonna stop here. What's the time? It's 15:23. So we can reconvene at 15:35 as usual.
Sounds good. Sounds good. 35. And since this is the last hour, okay, 35 plus 45. Okay, we finish at 4:20. It's good if we leave some time for questions.
Yeah, that's planned. That's already in the plans on the second part.
Very good, because there is no discussion session tonight, so this is the last chance to ask.
No worries. That's gonna happen. It's part of the plan. Yeah.
Very good. Okay, so we will reconvene at 3:35.
Excellent.
Very good. Thank you. So I think we can start. Are you ready, Danny?
I am happy to start.
Very good. Okay, so go ahead. And sorry, before you begin, for the last time, I remind everybody that tonight I will send an email to all the students with a short survey to fill about the school, just multiple choice. It's very easy to fill, just a few minutes. Please do that, and do that as soon as possible. And Danny, go ahead.
Okay, thank you. Okay, guys, welcome back. Then let's get into the very last part of our lecture, no, to conclude not only our series of lectures, but also the school. So this is the whole scheme, the whole diagram of what we have covered in these lectures. We've seen that inflation is a mechanism that cured the hot Big Bang framework. We didn't see this in detail, but I think that's well known. We saw pretty much in detail that generates the initial conditions of the universe in the sense of primordial perturbations, both scalar and tensor. Scalar fluctuations are the ones that we've actually measured very well in the universe, both at large scale structure and CMB and isotropies, and they fit very, very well the prediction from inflation. Tensors, however, which become eventually an irreducible background, gravitational waves, have not been seen. This tensor spectrum is pretty much looked for, no, in CMB modes experiments, but so far not observed. We also saw that you can add extra species, symmetries, or other aspects to enhance gravitational waves from inflation. And then during the reheating of the universe, scalar preheating, gauge preheating, or even if we didn't see it, but it's there, fermion preheating can also produce very large backgrounds of gravitational waves, but typically peak at high frequencies. Then we've also covered phase transitions, which lead to large gravitational wave backgrounds. And in the case of thermal era, the electroweak phase transitions actually become very interesting from observable point of view. And then we've seen cosmic defects as a possibility after a phase transition, and how there is an irreducible background, and also a very very specific background attached to loops in the case of strings, which is pretty large and observable. So I think we should be very satisfied. You know, we've covered really a huge amount of material, so we should be rather happy. We divided this in 3 blocks. I decided to divide this in 3 blocks. So I don't know if there will be a space in that survey that you are being asked to fill up, but if you want to give some feedback about the division of topics, I'm happy to hear it, because you know, when you face a lecture like this, it's always very difficult to know what is the ground level of many of you, and that's why, for instance, I decided to give basics of cosmology and general relativity, whereas I'm pretty sure other people maybe didn't want that, you know. So I'm always happy to hear, you know, the 2 sides and then try to adapt the content for a next occasion. In any case, we've covered a great amount of topics, so we should be, I think, really happy with this. The second, third, fourth, and fifth topics that form the second and third block constitute our understanding, our way of understanding through gravitational wave backgrounds of the early universe. But if you remember at the very beginning of the first lecture, when we were motivating the case, we said that there are astrophysical backgrounds, and these are emitted in the late universe. And we also said that if there is time, we could say something about that. And since there is a little bit of time, I'm gonna give you some brief introduction or brief details about these astrophysical backgrounds, and also, why not, about some of the experiments currently looking for gravitational waves and expected to look for them in the next 20 years. So first, the Astro Background. Remember, in the late universe, this is, of course, when galaxies are formed and can host compact objects, such as binary black holes. These are the signals, mostly, that LIGO Virgo have been observing, and there's a collection of them. And from the collection of them, what we realize is that actually the ones we've observed, which are of the order of 50 signals by now, officially, they correspond actually only to a very small part of a population, of a large population. And the ones we observe are actually characterized because those are the ones sufficiently close to us or emitting sufficiently strong gravitational waves such that in combination with their distance, we have the ability to detect at the individual level their signal. But we do predict that there has to be many of these binaries in the universe, just inferring this from the observed rates. So most of the binaries actually in the universe are unresolved individually, but they still emit gravitational waves as binaries orbiting around each other and eventually merging and so on. So the superposition of their signals at the individual level might be very weak, their signal, but the superposition is not that weak and forms what is called the astrophysical background. And these come in different flavors, it comes from different sources. Could be black hole binaries, neutron star binaries, and even white dwarf binaries. To give you some taste of how this is computed, let us recall that we have defined in the lectures the energy density spectrum of gravitational waves. And it turns out that you can write this also in a different manner in terms of what is called the characteristic strain. And this is what astronomers typically prefer. Instead of the cosmological notation we've been using, they typically refer to the amplitude in their experiments or in their observations in terms of this strain. But it's a simple mapping, okay? Now, in order to characterize the emission of this unresolved system of binaries, we need to characterize the co-moving number density of these guys per unit of redshift. No? We need to know how the density of this guy changes with redshift and then integrate overall redshift space to get the signal. So essentially there is a master formula that tells us the amplitude of this particular way of characterizing the energy density spectrum, which is the characteristic strain. So there is a given formula which, as expected, it comes from the integral over redshift, so over the whole expansion history of the universe, where you have a density of these binaries times the spectrum emitted by, on the average, by these binaries. This is a theorem, if you want, or a master formula that was worked out in a beautiful paper. I really recommend you guys to read it by Finney. And notice that here the spectrum we are referring is at the source frame. So this is the spectrum of energy per frequency emitted on the average. Okay, we are going to consider they are all circular binaries. We are going to forget here about the other characterizations of the binary pair. Well, this is the spectrum in a simplified manner in the source frame at the place of emission. This is why you have to note that there is this frequency here, which is the frequency at the time of emission, but that's different from the frequency we measure, which is redshifted. The frequency we measure is F. Okay. This energy density spectrum is a trivial calculation of general relativity. It's actually one of the first calculations one typically do when you study gravitational waves for the first time. You can find it in any textbook, essentially, of general relativity that covers gravitational waves. Essentially tell us that it's proportional to some power of the mass, where the mass is the so-called shear mass, which is this funny combination of the masses of the binary, and inversely proportional to this power of the frequency of emission. So now the last ingredient we need is to express the co-moving number density of these objects in terms of some quantities we can measure. And it turns out that if you think a little bit about it, what this means, at the end, this is like the derivative of the number of objects, the binaries, with respect redshift and respect their masses and volume. And essentially, mathematically, this can be identified with the merging rate of them times the mass function, the distribution of these objects in the universe as a function of mass. And then you pick up this derivative here, the derivative of the time and the time of emission with respect redshift, that has a trivial expression in standard cosmology. So essentially, you can compute very easily this quantity because the current observations of LIGO Virgo networks, they are putting constraints, they are characterizing all the time what is this merging rate based on all the rates, based on all the observations they do, they characterize the rate, and they are characterizing also the distribution of these objects, the probability of having a pair of objects with a given two masses. And essentially, you plug in that functional form in your master formula by Fini, and you have here the master formula for the characteristic strain as a function of frequency. So it predicts a universal power law dependence on frequency, and then you have to integrate in your distribution of masses and in your redshift history. What else? Yeah, I can give you one example for you to see how this really looks like. So since LIGO Virgo are characterizing actually the distribution of neutron stars and black holes, let's focus on black holes. This is the rate, the latest characterization of the rate by the LIGO Virgo collaboration. I think LIGO Virgo CAGRA collaboration, now that CAGRA is also joined the network. You see it's just a power law in redshift with some corresponding rate. This is the most important thing, this rate here at redshift 0.2, they give it as a reference at 0.2. So one can plug in the numbers you get from the observation from the observatories, the network observatories, and this is what you get. I'm showing you now some work in progress we are doing for the LISA collaboration, using as an input the mass function and rate from LIGO Virgo CAGRA network. We introduce it in that master formula, and then, we get these straight lines. And then to be more precise, to double check, here I'm showing the spectrum of omega gravitational wave versus frequency. What we do is we create numerical catalogs of these binaries following the mass distribution. And these catalogs, we evaluate the waveform emitted of gravitational wave from each individual pair in each catalog. And then we add it up. And this is what produces this noisy signal. That's in reality how the background really looks with all these oscillations. If you integrate a little bit over the frequency of these oscillations, you get this smoother in solid blue and red. And then if you use the analytical form I was showing you before, you get these straight lines. So essentially, this background is expected to be noise contributing pretty much within the LISA sensitivity band, as well as, for instance, for the Einstein telescope is not so clear, because remember that what is unresolved and what is resolved depends on the experiment. So the level of this unresolved binary background, it can only be evaluated at an experimental basis for every experiment. This is where I'm showing this for LISA. Okay. Let's give some summary and perspective of the whole topic. So gravitational wave backgrounds can be cosmological or astrophysical. The cosmological are the ones, at least in these lectures, that we are mostly interested in because they probe high energy physics. The astrophysical are still very interesting. They probe properties of the population of these binaries, but the cosmological background is considered the holy grail. And this is also considered by astronomers because everybody knows that the astrophysical background is going to be detected sooner or later. But the holy grail backgrounds are those that contain information about fundamental physics, fundamental interactions. Since the astrophysical backgrounds are guaranteed, that means they are going to act as a foreground in many situations. And hence, when we go really to the experiments, we have to learn, at least me as a theorist, I wasn't very handy in these kind of techniques until the very recent years where I've started learning about signal reconstruction. In particular, we've worked out an algorithm for LISA, for instance, in this example, to reconstruct automatically the power spectrum of any signal that you could have within LISA. This technique can be, of course, extended to other experiments. It's simply that has not been done yet. And there are other techniques that other colleagues are putting forward to do reconstruction of signals. For instance, here I'm reconstructing one of the two peak signature signals from preheating I was discussing in the third lecture. Of course, we also have to learn how to separate signals because within the same frequency window, there's going to be a superposition of different signals. And that's going to be a mess, no? Because at the end, your experiment only measures some noise and you have to filter out somehow the different contributions. So you can do that combining experiments at different frequency range. it's been shown that this can help, for instance, to break the degeneracies between merging rate of binaries versus the string tension of cosmic string networks. And you have to develop the ability to reconstruct signals over a foreground. And this is a major problem we are facing now in data analysis reconstruction that is still pretty much work in progress in the community of gravitational waves. The experimental landscape is the following. Currently, there are very strong constraints from the CMB on the tensor modes in general, typically associated to inflation, but you could say these are constraints on tensor modes in general in very low frequencies, those corresponding to cosmological scales. There are constraints from pulsar time arrays, interpreting that, of course, the signal they have measured is yet not a background. And there are constraints from LIGO and Virgo network because they haven't seen any background yet. Okay, so these shade curves, these rule out any background there of gravitational waves. And then there are constraints from the number of relativistic species, both from CMB and Big Bang nucleosynthesis, but CMB is now more competitive. The landscape of experiments within the next 10 to 20 years is going to look like this. The PTA experiment, so I'm leaving aside the CMB, which is very low frequencies, okay? We are focusing only on frequencies from 10 to minus 10 Hertz to above. PTA experiments are going to improve a lot with SKA after a number of years taking data, is expected to reach the sensitivity. So we really hope there is a huge room for discovery of gravitational wave backgrounds. Then there is LISA, then there is Einstein telescope, and then there are other proposals, like a network of atomic interferometric devices, which of course are a proposal just, not in the same level yet as LISA or Einstein telescope, or other proposals like lunar laser ranging or satellite laser ranging, which is very recent from just a few months ago, and essentially cover a bit this gap that we had historically. There are more futuristic proposals, certainly in the case of BBO, Big Bang Observatory, which is like a bunch of LISAs together. We don't know if this will ever be realized, and there are interesting proposals also in atomic interferometry, which I think altogether gives a nice perspective that sooner or later we are gonna really cover very well, the frequency landscape of gravitational wave backgrounds. Altogether, this is the picture I think we expect to reach eventually. I doubt we get in the BBO will happen after the 230, so if it happens, okay. So let's say forgetting about BBO, the rest could be maybe the picture we get in 15 years time from now, okay, which actually shows that either we get a detection or we start ruling out a lot of high energy physics phenomena from the early universe. The CMB has been improved a little bit. I recommend you to look at this paper if you want. This is the real constraint in the spectrum per frequency bin at the frequency scales. Here you have it in Hertz corresponding to the CMB. And the final plot I want to show you is as it came out in the session of questions yesterday, there has been the claim by several PTA collaborations, pulsar timing array collaboration, that there is a unknown stochastic noise that they detect coming apparently like from all the pulsars, but it doesn't verify yet some of the minimum standards of statistical significance, in particular for a specific spatial correlation that is mandatory to be verified for this to be identified with a background that has nothing to do with the pulsars themselves or with our systematic errors in some way. So cosmic string network could easily explain this signal and yet be out of LIGO, even in the improved final LIGO design work. But you see, if this was the case and we measure the spectrum eventually with PTA experiments very well, then there should be a very nice correlation, if this is the case of cosmic strings, with other experiments coming in the coming years. And this is going to be at the end the way to disentangle what's the origin of any potential signal we will measure. So with this, I think I've really, I want to conclude my set of lectures. I think we've covered quite a lot of topics, including a little bit, not much in detail, but a little bit, the Astro Background and observations of gravitational waves. What we've seen in the course is that there is a complicated but robust way of defining in a meaningful manner gravitational waves. What we've seen is that gravitational waves from inflation, from vanilla models of inflation, the irreducible background from quantum fluctuation, there is an intensive search of that background at the CMB. And if you add extra ingredients, in particular and shift symmetry, this is really very appealing case, or also if you put ultra slow roll or other aspects to enhance scalar perturbations to enhance your gravitational wave background from inflation. From preheating, it's very standard to get a high amplitude background gravitational waves, but very unlikely to have a detection so in any time soon, because these are peak at high frequencies. From phase transitions in a dark sector could peak at any frequency, especially at high frequencies if they are high energy scale phase transitions. But the electroweak phase transition is if embedded within BSM extensions of the standard model, would provide us an observable signal within LISA. It's just in the natural frequency ballpark of LISA. And the case of gravitational waves from cosmic strings in the non-Bugoto approach, this is important to be considered. It's certainly a very good case of a study because there are orders and orders of magnitude we can prove of the tension. Let them be these strings from GATT scale, or from GATT theories, or from whatever other BSM scenario. And finally, we've also seen that the Astro Background provides a foreground, and what we have to learn really in the next decade is how we manage to disentangle signals from primordial origin to astro origin, and then signals among themselves. To conclude, a piece of propaganda in case you guys want to introduce yourself as at a technical level. Well, my colleague Chiara Caprini and myself, we did an extensive review, it's close to 200 pages, on the basics of gravitational wave sources and the basics of gravitational waves themselves. This is the leading review in the community now, so I invite you to have a look, and surely if you have any doubts or you find any typos, let me know. And a piece of propaganda, part 2, is that in case you are interested in numerics, we have also finished what I really consider kind of the work of my life, because I started this when I was a PhD student and I finished it last year, a code for simulations that essentially allows you to do essentially any field theory simulation you want to do. Okay, you just have to learn how to use the code. This code is called Cosmolaris. It allows you to introduce a physical problem characterized by some initial conditions and some type of equations of motion that you decide. We have a variety of equations of motion right now, but you can add others. You choose your parameters, and then it produces automatically, if you can run in a cluster or in your laptop, a bunch of observables. If you have a new physical problem, you just need to introduce it through new equations of motion, because essentially the idea of Cosmolaris is this is a platform for field theories. So essentially, it's not a code for a specific problem like preheating or cosmic strings or phase transition. It's like a library or a code where it has enough flexibility that you can try to choose the problem with the current tools, or introduce your own problem if you become an expert on using it. The current public version that we released last year already deals with the scalar gauge dynamics of U1 and SU2 interactions. It's parallelized in multiple dimensions, but you write in serial. So even if you are not an expert programmer, you can write this in a very simple manner. It has a family of integrators already, so you don't even have to choose to design yourself an integrator. And it's written in a modular manner such that if you want to add new things, you can add them. And it uses its own symbolic language and field algebra, which means that there are a bunch of operations like how fields or derivatives of fields occur that are already defined. The upgrade we are planning is to add gravitational waves Hopefully this will happen in February or March, because it's already done. We just want to make it public in a clean manner. We are also done with adding an Axion-like coupling of a FF dual gauge sector. We are going to release only the abelian case first, but it's straightforward actually to generalize to non-abelian. We've already finished a non-minimal coupling to gravity. We released the algorithm in a paper, but we haven't made public the code yet. We'll do it also in the coming months. And we also have it ready for cosmic string networks, which we will also make public hopefully this year. We've added now new integrators and arbitrary new initial conditions, which essentially makes the code even more powerful to handle almost any problem you want. But we don't have yet fluid dynamics, for instance. You know, I'm hoping to hire some postdoc or PhD student for next year, and we can start adding these kind of tools into the code. And finally, just one comment, in case you are interested in learning about using this tool. I got money recently to organize a school. So I'm really hoping to organize a school on Cosmolaris in this year, by summer or most likely fall. But I wanted to do it in person. So if pandemia does not permit for it, maybe I will wait another year, because I definitely recommend you to come visit into Valencia. It's one of the best places in the world to live. I can tell you this from experience, and I'll be very, very happy to have you guys visiting here in what is now my hometown. Having said this, after 100-ish slides or more, I can thank you for your attention, and I'm very happy to take questions if you have some. Thank you, guys.
Thank you, Danny. We thank you for the lectures. People clapping, but with the microphone muted.
I hear some, it's okay.
Thanks so much. And now we can open the last session for questions. I see there is already a raised hand by Car. Yes, please go ahead.
Yeah, hi. Thanks. They were really good lectures. I've learned way more than I thought I would ever learn about gravitational waves within a week. So thank you very much.
Thank you.
But my question relates to actually this lecture, when you were talking about the cosmic strings that have a Nambu-Goto strings.
Yeah, they have a width. They have a width.
With a width, yeah. Can you explain in like a more technical sense what goes wrong where it becomes like a poor approximation, or you start opening
well, it's not clear if anything goes wrong. Be careful. The problem is the following. For 30 years, people have been working out these predictions from the Nambu-Goto point of view. And then at some moment, computers got powerful enough that people started doing simulation of networks in field theory. And then we got the surprise that you use it to maintain scaling. The picture both in Nambu-Goto and in field theory, so in general for cosmic string networks, is that the strings intercommute and then chop off loops. So it's the fact that you lose these loops from the network that makes the network to maintain scaling. Now, the idea in Nambu-Goto is that once you produce these loops, you lose that energy in gravitational wave radiation, because that's the only channel you have, since you are not describing what the string is made of. You are essentially using the Nambu-Goto, which is the action of a relativistic string. It's the same starting point when you do a string theory, fundamental string theory, okay? So essentially, that infinitely thin string has no structure, but gravitates. So people computed what's the gravitational wave emission. Now, when some people before me started doing field theory simulations, what they started seeing is that, yes, you form the loops and your whole long network of strings go in scaling, but these loops, they decay into radiation of the actual content of the matter content that the strings are formed of. So in these simulations, we are literally simulating a physical scalar gauge theory. Okay, it's not like we are doing any approximation. However, it's true the simulations are limited to a given separation of scales. We can separate the width of the strings and the typical separation no more than 3 to 4 orders of magnitude. Okay, once we reach that, then the simulation is kaput from the physical point of view. We cannot continue. So the argument of a Nambu-Goto community is that if we were capable of simulating for bigger scales, which actual computers are not capable, because these simulations are already very costly, then you would start seeing that the loops do not decay into their quanta, into their own quanta. It's true that from a physical point of view, it was not expected that they would be radiated away, because since this phenomena of string formation comes from symmetry breaking, you are giving a mass to your gauge boson here. And also your Higgs sector has a mass. So these are massive guys, and you wouldn't expect to radiate them. But it's also true that inside the string, they are massless. So I think that's the part that the Nambu-Goto approach was not counting for. So what is clear is that when you do field theory, you open up new channels. This has been seen in the simulations, but different peoples, independent groups. So it's clearly a physical effect. Now the question is whether this physical effect remains when you manage to separate more the scales between the size of the strings themselves and the width, you know, and that's the discussion we are having all the time in the community, and people don't agree.
Okay, thank you. Yeah, so it's the substructure is like too big when you're running the sim. Okay, yeah, thank you very much.
My pleasure.
Who is next? I think Leonardo, the order says Leonardo.
Okay, sure. So thank you, Daniel, for the very interesting lecture series. I too learned a lot. So I have a question on the relationship between gravitational waves from cosmic strings and Axion dark matter. So would it be possible for you to elaborate
yes, of course,
a bit on the connection?
Let
so specifically, I'm interested in knowing how to convert, for example, projective sensitivities from LISA, etc., in the usual Axion dark matter plot. So for example, for Axion to FF dual.
I don't have that connection in the transparencies, okay? But as you know, an Axion-like particle is a very good candidate for dark matter, simply from having a mass, no? And once it oscillates, it behaves really as a matter-like, and hence that's a good candidate for the dark matter. Now, in the different mechanisms in Axion cosmology, as you know, if you are familiar with the axionic dark matter, it's very common that this comes from asymmetry breaking, and then you form global strings. And these are called axionic strings, but at the end, these are the same as global strings of a scalar field, okay? So essentially, you can simulate these global strings in lattice simulations. This is where we also have discrepancies between, for instance, my group and these other groups. Of course, you know, typically when you focus on this work, you mostly characterize by the tension, no? What is the emission of gravitational wave background? So now you have to relate that tension to whatever aspect of the dark matter you want this model to represent. I don't know on the top of my head that relation, but I believe in Gorgetto et al., for instance, you can find these relations. That's my belief. But I wouldn't be able to tell you now on the top of my head how to relate the specific windows for dark matter with the observability on gravitational waves. But it is clear that for the windows of validity of Axion being dark matter, there are presumably windows of observability of these gravitational wave backgrounds, although modulo, this depends on what's your approach to compute this gravitational wave background, okay, which is very difficult to do, unfortunately. Again, because of problem of separation of scales.
Okay, thank you.
Thank you.
Okay, next one is Angel. Bye. Go.
So I was trying to understand these cosmic defects and the emission of gravitational waves.
Mm-hmm.
And so I have two questions, but I think that the answer for one question is also the answer for the other one. So I was trying to understand if these structures are stable or not.
Mm-hmm.
And if they are stable, why? Because I don't understand that. And also the other question is if the emission of gravitational waves happens only in the formation of those effects or also after the formation of those effects.
these defects are stable because the stability is guaranteed by the topology of the vacuum manifold. There is, look at this, you know, this is a Higgs configuration where the Higgs is wandering around, okay, the phase is wandering around at 2 pi, you know, circulation, and then you have your cosmic string here. Now what's going to happen as dynamics go on is that the strings are going to start separating from each other. There's nothing in the dynamics to unwind this Higgs configuration. You see, you cannot undo the strings. That's also why it became a surprise in the simulations. Once you form the loops, they are capable of decaying completely in their own radiation, you know, because a priori you would have thought that, you know, they are also stable, but in reality, if they emit their own quanta, now you make them disappear, not by overtaking the topological obstruction here, but just by making their energy go away into another channel. So for the long strings, however, this emission of quanta doesn't happen in a significant manner. And then essentially, yes, they are stable objects. Okay, they are stable objects. If you think them, you can view them like that, as they are normally represented. They are objects, whatever they are made for. Or you could plot the three-dimensional distribution of the Higgs field and the gauge fields everywhere in space. And what you would see is that, do I have a transparency to show you this? What you would see is that as the strings separate, the space in between, the Higgs is simply a continuous field circulating in its manifold, but then suddenly arrives to another string, and then it circulates to pi, you know, and then goes to another region, and it goes smoothly until it finds another 2 pi circle. So you cannot undo that, and you are simply making the separation of these stable objects grow. And now your question whether they produce gravitational waves at formation or later, both. You know, during formation, that's a phase transition. So essentially, for instance, the peak we were seeing of gravitational waves from gauge fields in a phase transition yesterday, that is the peak from the fact that we were forming cosmic strings. Okay. But in reality, you know, at that moment you don't care because you have a blurry distribution, so you don't differentiate yet there are strings. As the transition completes, in the sense that in between the strings, the Higgs is really fixed in the vacuum manifold, then you start seeing the motion of these strings like if they were individual objects. They enter into the scaling regime, and once they enter there, they start emitting gravitational waves as a whole network. And then they start chopping off loops, and at least in the Nambu-Goto view, that contributes to a significant gravitational wave background, which happens all through cosmic history, which is the reason why this spectra, and this is one of the few cases together with inflation, is extended in so many frequency decades, because these are the emissions from the loops at all different parts of cosmic history. You see, we just go accumulating them. All right.
Okay.
A very special
Thank you very much.
Yeah, my pleasure.
Okay, there is Gonzalo now.
Hi. Yeah, thanks. Yeah, thanks for the lectures. It's been very, very interesting. I wanted to ask a question. When we were discussing inflation, you mentioned that the gauge field excitations source gravitational waves, and you talked about a blue tilted spectrum. Okay, yes. I get that. You mentioned it was also chiral and non-Gaussian. So yes. that made me wonder, what are the features we can measure about a gravitational wave background? How can we differ one from other? Yes. Or how can we characterize them?
Yes, here is the background you are talking about. Yes, this background was from gauge fields that were coupled to an axion-like inflaton. So it comes from an axion times FF dual interaction. And they were chiral in the sense that only one of the chiral polarization of gravitational waves is activated, because only one of the chiral helicities of the photon is activated. They are blue tilted, that's what it means, simply a rising spectrum with frequency. And they are non-Gaussian because in the moment you have an active source of gravitational waves, any source is from the energy momentum tensor, which is a bilinear in fields. So the 3-point function of tensors is naturally the 6-point function of fields of the source. And the 6-point function of the source is non-zero, no matter whether it is Gaussian or non-Gaussian the source. So that means that the 3-point function of a source gravitational wave background is always non-zero, and hence is a non-Gaussian background. Okay, that's what I meant. Whether we can measure it or not, there's been few papers on this in the literature in the very last few years. Only very special cases. You need to correlate different detectors, and you need backgrounds that are really of higher amplitude than the ones I've shown you. So it's not clear if there is any physical prediction motivating those backgrounds. So technically it's possible. In practice, it's extremely difficult. But I believe that, we'll have to go by parts. I think the first observable we really want to measure is the power spectrum. If we do measure eventually a power spectrum of a stochastic gravitational wave background, again, I'm pretty sure we will start thinking, with more attention into what do we really need to measure chirality. And non-Gaussianity also is very difficult to measure it. Mostly in any cosmological background, it's suppressed from the expansion of the universe. You lose the non-Gaussianity. This is very different from the CMB, where the fluctuations, when you measure them, correspond honestly to the moment of horizon crossing at decoupling. And that means that you are probing both super horizon and sub horizon, but all around the horizon scale. Whereas the scales we are probing here come from gravitational waves that have been traveling at sub-horizon scales really all the cosmic history, and the 3-point function picks up a random phase and then kills this intrinsic correlation I was telling you. So again, there are few cases where we could discuss measurement of non-Gaussianity, but I haven't found yet any appealing case or anything I believe. I think it's gonna be the physics of next generation of physicists once we detect any of these backgrounds. And eventually we will need these kind of things because they will be observables helping us to differentiate one background from another. For instance, another aspect that is not here is that some of these backgrounds could be anisotropic. So if I have a detector that measures the energy density of this background in one direction, then it could be that we measure in different directions and that energy density spectrum fluctuates pretty much as the amplitude of the CMB temperature. So if we measure those fluctuations, there are predictions for the astrophysical backgrounds about those fluctuations. And there are some few very specific models from early universe that also have cosmological fluctuations. And that would be another way to differentiate the possible origin of one background from another. It's all potential ideas, far away, I think, at this moment from, really thinking that they are going to help us to differentiate any of the cosmological backgrounds. Certainly, it would be very helpful, the anisotropies, for instance, for the astrophysical backgrounds, to break the generacies with potential cosmological signals.
Okay, very illuminating. Thank you. Thanks a lot.
My pleasure.
Any other question before we close this lecture and actually the school? Aaron, please go ahead.
Hi.
Hello.
I had a question. So you mentioned that for topological defects, or any defect that in general, that the spectrum is scale invariant, right?
Yes.
Okay, but there is some paper from some Japanese people. I think they are called Saikawa and Hiramatsu. I don't know if you know the guys, but there they discuss some spectra from domain walls, and there it seems like it's not scale invariant, that it is in a different kind of spectrum. Do you know anything about it, or do you have some comments about them?
Yeah, I think I'm not sure about what paper you mean, but there are few papers on domain walls. The most known paper on gravitational waves from domain walls, which is from a Japanese group. I'm not sure if it's the same people you are referring to. It's the paper about the actual formation of the domain walls. So it's a single peak spectrum. Then there is another paper on domain walls and general global defects, where they use the machinery we use to predict scale invariance, but they compute it now assuming there is a matter-dominated background in the early universe. So that breaks the scale invariance and introduces like a broken power law. I'm not sure if that's the paper you are referring to. Those are the two that come to my mind. But in general, from descaling, so the later evolution of the network one is really well formed and it evolves all through cosmic history. It is expected from the scaling argument that the background should be a scale invariant. And you would only break this scale invariance of the background if there is some breaking of the scaling distribution of the defects, which is the claim of some of the papers on Axion strings.
Yeah, and which mechanisms can break the scaling regime? If you can.
That's a that's a good question. I don't know, because I would say that the scaling, is kind of expected. For instance, colleagues of mine have the interpretation that these other simulations where they see log deviations of scaling, they interpret this as related to the initial conditions of the setup of these simulations, where simply takes longer to reach into scaling. And actually, if you do Nambu-Goto so-called velocity scale modeling, where you adjust some parameters and you do some analytics, you do predict that in that regime, the time scale of scaling will be comparable of the time scale of your simulation to arrive to scaling. So it's normal that you don't see the full scaling and you are on your way towards scaling. And there is interpretation here that the deviation from scaling they see is a log correction to scaling, or there is interpretation that they are just on your way towards scaling and you just haven't achieved it yet. But there is a hot debate there.
Okay, thank you.
Thank you.
There is time for some last question in case you have any. Okay. I don't see any questions, so I think we can close here. Oh, sorry, there is. Yes, go ahead.
How did the universe
begin? So it's a question on something that I don't think has been mentioned. For example, gravitational waves from instabilities due to superradiance effects from, say, ultralight dark matter.
Yeah, that's very interesting.
Right. So would you like to perhaps say a few words about the possibility of using future interferometers to set limits on certain dark matter models or anything like that?
I mean, maybe you can comment on that, because I don't. Again, it's a very interesting case, but I don't have on the top of my mind the constraints you can infer from that. So I don't want to say nothing stupid. Certainly for these dark matter models, it's very interesting to think that you can produce these clouds of superradiance, and hence you produce a background and you put constraints from the lack of observation of this background into the fundamental coupling involved in the model. But I don't know on the top of my head the connection again with the dark matter modeling, so I prefer not to comment on that. Unless you know the numbers, you are very welcome to tell us.
No, I don't know the numbers.
Okay.
But thank you.
Thank you for the question. It's a good question anyways. I recommend you to have a look into those cases too, guys. Super radiance from Axion clouds, is from late universe emission, but it's interesting because you can put constraints on fundamental physics.
Thank you very much, everyone, again, and
take care, everybody.
Hopefully in person soon, somewhere in the world.
Everybody.
Bye bye.
Thank you.
Bye.
Very much.
Bye.
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 Thanks.
Thanks a lot.
Ciao.
Ciao.